Okay, good morning. We'll start sharing the screen. So, okay, good morning, everyone. So, the last class we had seen how the ruin problem concerning the Kramer-Lundberg network, Kramer-Lundberg process can be handled in terms of a random walk, which is manufactured out of basically that skeleton process corresponding. That is basically the risk process are evaluated at the arrival time. And so the random walk we are looking at, and our objective is to get some kind of a bound for the ruin probability. We had also seen that without the net profit condition, ruin is certain. Probability of ruin is 1. Probability of ruin in finite time is 1, however large the initial capital might be. And to get a bound, we had defined what is meant by adjustment of Lundberg coefficient, and also we had shown or proved a proposition which gives a set of sufficient conditions. This is MZH. You may recall that it is e to the power h times that is Z1. That is xi minus c times ji. Okay. So proof of this we had seen the last class. Yeah, using convexity and things like that. Yeah. So today we will proceed with that. Well, if a random walks comes into picture, can a martingale be far behind? So we will encounter a martingale. So consider the Kramer-Lundberg risk process. Assume the net profit condition and that the Lundberg coefficient exists. This is the unique R strictly bigger than 0 such that the moment generating function evaluated at R is equal to 1. And we had given sufficient conditions. Okay. So let ZL and the random walk Hn be as in the earlier results. Yeah, please. You can note it down if you want. And you consider e to the power r times, that is e to the power r times Hn. R is the Lundberg coefficient, and e to the power r times Hn, as n varies from 0, etc., is a martingale with respect to the sequence, IID sequence Z. Okay. Proof. So it's clear that e to the power Rhn is a function of the Zi's up to n. And since each Zi has a moment generating function in a neighborhood of 0, let's say the neighborhood determined by, let's say, h0 greater than 0, it's clear that each of these e to the power Rhn has finite expectation. So the appropriate measurability or this condition dependence and the expectation exists. These things are satisfied. Now, we know that the Zi's are IID random variables. So Zn plus 1 is independent of Z1, Z2, Zn. And of course, Zi's are IIDs. So one can verify for each n running over 0, 1, 2, etc. The following happens. The expectation of e to the power r hn plus 1 given z1, z2, zn. We have to show that this is equal to e to the power r hn to prove that the object is a martingale. So the proof is quite simple now. You write this as e to the power r hn times e to the power r z n plus 1. So this is function of all these things. So using the properties of conditional expectation, so that comes out of the conditional expectation thing, like a constant. And what remains is conditional expectation of e to the power r zn plus 1 given this. And now, because of independence, this is just the unconditional expectation. And the Zi's are IID random variables. So expectation of e to the power r zn plus 1 is same thing as expectation of e to the power r z1. And since r is the Lundberg coefficient, this quantity is precisely is equal to 1. So in the last step, we have used that r is the Lundberg coefficient or adjustment coefficient. So this is a fairly simple result. Of course, all the kind of non-triviality is contained in getting the appropriate definition and this thing about the Lundberg coefficient. That is where the, let's say, if you happen to, or if you can come across the correct apt definition, of course, to come across this kind of a thing, it could have taken years of trial and error and so on. Okay, please note it down. So we will now prove the desired bound. The assumptions are as before. Then the Ruin probability is less than or equal to e to the power minus r times x. So for all x strictly positive, note that this is strictly less than 1. Because r is positive and you have a negative sign here. So this is what we had hoped for. If the net profit condition holds, that we wanted the Ruin probability to be hopefully less than 1 for positive x. Actually, with more work, etc., this can be improved. I will just mention certain things after, little later. So now we have been using certain things which we have seen the last semester, like random walk we have brought in, martingales we have brought in. So now one more thing from the last semester, you will see a kind of a concrete application. Sorry, please note down few. So let x be a non-negative number, arbitrary but fixed. So this is going to be the initial capital. So R0 equal to x is the initial capital. Now we have that random walk Hn, and we are interested in supremum of Hn exceeding x. So to handle that, now define sigma x equal to infimum of all n's greater than or equal to 0, such that Hn is strictly greater than x. So given the initial capital, this kind of event would contribute to ruin. That we have seen. So if there is actually an n which satisfies this, then it is the infimum of that. If there is no such n, then sigma sub x is infinity. As you would have guessed by now, verify that this sigma sub x is a stopping time with respect to that Zn. And sigma sub x takes value in non-negative integers and of course possibility of plus infinity. Yeah, verify also that the ruin time tau 0 less than infinity is same thing as sigma x less than infinity, that event. So we know that the ruin probability psi of x, that is probability of tau 0 less than infinity given R0 equal to x, given the initial point is x, that is the initial capital is x. Now this is sigma x is something which is manufactured out of the Hns, and H0 is 0. This thing when starts from 0, Hn. So this probability is same thing as probability of sigma sub x less than infinity given H0 is 0, which we shall denote by P sub 0 sigma x less than infinity. So in other words, to study this, we need to study this. And that is where the stopping time comes into picture. Yeah, so we have. So let k be a positive integer. Then you can easily see that the minimum of, say, any k is a stopping time, any constant k, and sigma x is a stopping time, and the minimum of the two stopping times is again a stopping time with respect to Zn. Moreover, this stopping time is bounded by k. So it is a bounded stopping time with respect to Zn. Of course, it is bounded even though this is possible, because for all those sample paths for which sigma x is plus infinity, this stopping time would assign the value k. So one can, another result from the last semester, the optional stopping time, optional stopping theorem. Optional stopping theorem applied to this martingale. We have shown that in the last result, e to the power Rhn is a martingale, and here we have a stopping time which is also bounded. So by the optional sampling theorem or optional stopping theorem, the expectation of e to the power R times this is equal to this. This is the first equality, is where you apply the optional stopping. And H0 we know is 0. So yeah, so this is equal to 1. Okay. So we will write this as, we will split this thing into sigma x less than k and greater than k, less than or equal to k and greater. So the left side of this expression, this is precisely that thing. First, you take the expectation when this is confined to this set. So this times the indicator function of sigma x less than or equal to k, and this for sigma x greater than k, this object becomes hk. So note that what you have here is precisely this left side. Convince yourself. But by the definition of sigma x, this object h at sigma x is strictly bigger than 0. So this expression is bigger than just this expression because this is non-negative. And coupled with this, we get e to the power Rx times indicator of this set, that expectation of that is less than this first term here. So which term is less than or equal to 1? Now note that this is a constant. So that comes out of this expectation. And what you have is expectation of the indicator set. So that is nothing but probability of this event, that set. So that is what we have here. here this is a constant, so that comes out, and the expectation of indicator of this set is probability of that set. So that is P0 sigma x less than or equal to k. Now the next step, we will take this guy to that side. Then you get the e to the power minus rx. So therefore, we have P0 of sigma x less than or equal to k is less than or equal to e to the power minus rx. For any x. So you are seeing some concrete applications of certain results which we had seen last semester. Okay, please note it down. So the right side is independent of k. So let k go to infinity. Then you get P sub 0 sigma x strictly less than infinity is less than or equal to e to the power minus rx. That is psi of x less than or equal to e to the power minus rx for all x. So this completes the proof. So this is applies to fairly large class of xi's, that is the claim sizes. The assumptions we are making are the expectation exists, and also of course later the moment generating function exists in a neighborhood of 0. And also the net profit condition should hold. So the premium is chosen so that that holds. So net profit condition holds, and this should have moment generating function in a neighborhood of 0. And of course, that Lundberg coefficient should exist. There is no kind of distribution type assumption on xi that it has to be of this kind of distribution, that kind of. However, in the context of insurance, distributions or claim sizes, some of them may not even have variance. Those are also important, but we will not look into such things. So this completes the proof. It's a fairly important kind of situation. And there one gets some kind of a handle using certain things which we have seen last semester and this semester. make some comments. See, actually, this psi of x, we can show that this is strictly less than 1 even when x is equal to 0. So even with 0 capital, if the assumptions of this theorem are satisfied, there is a probability that the ruin might never happen. That is, with some more assumptions and of course more work, one can show there exists constant C1 and C2, because 0 less than C1, this is strictly positive, and this one, and this is strictly less than 1. This is quite important. So this kind of a result gives you a two-sided bound for the ruin probability. And if you put x equal to 0, till you get that here, this is 1. So C1 is greater than or equal to, less than, C1 is less than or equal to this, means there is always a possibility of ruin, positive probability of ruin. And here also it is 1. So this gives you, even with psi 0, it is less than or equal to 1. Sorry, strictly less than 1, since C2 is less than 1. So that's why in particular, psi 0 is strictly less than. Whereas the net profit condition doesn't hold. However large this psi of x is, this will be 1. And in addition to this kind of two-sided bounds, results on the asymptotic behavior. So here, of course, you can say from this itself or even from here, that is as x goes to 0, this goes to 0. But to determine more precise asymptotic behavior, that is, you get hold of some function so that psi x divided by that x goes to some constant. Such kind of results. That's what meant by asymptotic behavior of this. So that even for large values of x, it behaves somewhat like that. I think in that kind of result, even there, this will play a role. E to the power minus Rx will play a role. However, exact expressions for this are known only for a very limited classes of claim size distribution. Okay. If you want me to go back to any of these things today or last class, please ask. Okay. So before ending today's thing, I will make some comments. So in the last couple of classes, we have been discussing ruin, the phenomenon of ruin. And that has been concerned with the following type of scenario. By our net profit condition, expectation of Z1 is strictly less than 0. So denote expectation of Z1 by mu. And the definition of ruin or probability of ruin is probability supremum over n, Hn, exceeds level x. and for x, positive. So x is certainly bigger than mu. And not only that, this x can be possibly very large. So in other words, x can be very, very far away from mu. So since this is mu, see the Zi's or Zn's are made out of adding up these Zi's. Yeah, HI, sorry, HI. The random walk is made out of adding up these Zi's. So by strong law, the asymptotic behavior of Hn would be hovering around the mu. I mean, n times mu rather. Hn over n goes, as n goes to infinity, goes to mu. That's what SLLM says. That is, after some time, I mean, the Hns are more likely to be on the negative side. Whereas here we are interested in an event which is against the current, against the trend. And such an event is only ruin. So ruin is an event where this process which is going to be going towards negative infinity, what are the chances that it would be found far away on the positive side? So these kind of events happen when the Hn, the random walk, is far away from its mean. Such events are called rare events. Of course, in the context of insurance, as you all know, we would like the ruin to be a rare event. That is why one is interested in probability of such events. So that the ruin company, I mean the insurance company, is in a position to honor any genuine claim. So study of probability of such events is, such events are asymptotics of such probabilities, etc., are known as large deviation probabilities. And Lundberg bound and extensions, various extensions, some of the other two-sided estimates, etc., are basically due to Kramer. And also the asymptotics. Asymptotic results are due to Kramer. I don't think Lundberg and Kramer collaborated, because I think they are perhaps separated by about 20-30 years. So Kramer extended or polished many of the results due to Lundberg. These things are known with both their names put together. So these are rare events. The typical events are The results concerning with typical events are the strong law of large numbers, central limit theorem, etc. Where basically the events of interest are close to the mean. Remember, SLLN says that Hn divided by n goes to the expectation. So in other words, as the n becomes larger and larger, that ratio Hn over n, one can expect it to be very close to the expectation of the each summit. So in other words, Hn will be close to n times that expectation, roughly speaking. So those kind of things are typical events. Similarly, central limit theorem, if you take the sum, or rather you centered sum, that is you subtract the mean and take the sum and divide it by the appropriate scaling level, root n times something and so on, that goes to the normal distribution, standard normal distributions and on certain conditions. Second moment should exist and things like that. Yeah, so that is all for the day. And yeah, if you want me to go over any of the previous slides, please ask me. Okay, we'll stop sharing. So yeah, that is all what I wanted to say concerning the Cramier-Lundberg this thing, and also compound Poisson process. So these notes I will put on Moodle after your midterm is over. Next week, since it's a midterm week, there will be no classes. And soon certain communication regarding the midterm I will be sending to you people. Concerning, I want to make the maximum size of the file to be 8 MB and things like that. So such things I have to do. And also the question paper will also be put up as an assignment on Moodle. Before that, I will, just a few minutes before that, I will send the question paper to all of you through that alias address. And so wish you all the best in all the exams next week. So Wednesday, we will have that exam. And after that, the class will be hopefully the Monday following that. All of you take care. All the best. And thanks a lot.
Thank you, sir.